Hello everyone, in today's video we'll be solving the questions of the previous year physics optional exam. So let's start the first question. Here we are given the two capillary tubes, one of length 2L and other with length L, and so they have internal radii, different internal radii, this is R and 2R respectively. So when water is flowing in streamline, the pressure difference across the first capillary tube is given P. So we have to find out the pressure difference between the ends of the second capillary tube. So let's start with the solution. So this will be, so we are given the pressure difference in the first capillary tube to be capital P. So we have to calculate this pressure difference in the second capillary tube. We are given this length to be 2L and R radius, and this is length L and 2R radius. So we know this the junction, the rate of flow will be same. So here Q is the rate of flow. So we will be using this condition to solve this question. So firstly we should know the Poiseuille's formula. Which gives that the rate of flow is directly proportional to the pressure difference into pi and the fourth power of the radius, and this 8 eta is the viscosity of the liquid, and this L, this is the length of that tube. So this is the formula. So we will be using this formula. So in the first tube, this is our first tube, this will be our second tube. So let's find out the rate of flow through the first tube, which is given as delta P1 pi R1 4 and this 8 eta L1. Here delta P1, so this is pressure difference across the first capillary tube, which is given as P. R1, the radius of the first tube is R, and the L length is twice of L. So we will put all these values. So our expression will become 8n twice of L. So this is Q1 P pi R4 by 16 eta L. Similarly we will find out for the second capillary tube. This is Q2, this is delta P2 pi R2 4 and this 8 eta L2. Here the length is L, radius is twice of R, and we have to find out this pressure difference. So let's put the values. So this is delta P2 pi twice R4 and this is 8 eta L. So twice to 4 is 16 pi R4 delta P2 over 8 eta L. So this will be twice pi R4 eta L delta P2. So this is our, and we know the condition Q1 is equal to Q2, the rate of flow will be same. So let's equate these two. So Q1 is pi P pi R4 16 eta L and Q2 is 2 pi R4 delta P2 eta L. So this will cancel out, pi R4. So we are left with delta P2 is equal to P over 32. So this will be the pressure difference. So let's move to next part, that's the D. So here we are given a water drop of radius 0.04 mm is falling through the air. Here air is a viscous medium through which the water drop is falling. So we are given the viscosity for air and we have to find the terminal velocity. Before solving this we should know what is the terminal velocity. So terminal velocity is the maximum constant velocity acquired by body while falling through the viscous medium. So in this question our viscous medium is air. So let's say this is a body, this is a water drop which is falling through the viscous medium. So because it is a viscous medium, this water drop will experience some drag, viscous drag. So let's say this viscous drag to be F, and there will be upthrust because it is a viscous medium. So let's say this upthrust to be U, and there will be a gravitational force mg will be acting on this. So let's balance out these forces. This mg will be balanced by this upthrust plus viscous drag. So mass, so let's say this density of this water drop be rho, and the density of this viscous air to be sigma. Volume of this drop, water drop, and this multiply by this density, this will be mass, and into gravity, and the upthrust will be 4, the volume, and the density of this viscous medium will be sigma. So this is the mass into gravitation. So this will be a upward thrust which will be experienced by this water drop, plus the viscous drag which is given as 6 pi eta rv, where v is the terminal velocity. So let's solve this. So this will be 4 pi r3 rho minus sigma g upon 6 pi eta r is equal to v. So we will cancel out this r, this will become r square, pi with pi, and this 3 with 2. So our final expression for terminal velocity will become 2 over 9 r square over eta rho minus sigma g. So this is our expression for terminal velocity. So let's start solving this question. So we are having our expression for terminal velocity is 2 by 9 r square eta rho minus sigma g. So we are, our rho is a density of water because our body is a water drop, and sigma is the density of viscous air. So we know the density of water is very large than sigma, so we can neglect the sigma, and know rho is 1000 kg per meter cube, and we know sigma to be approximately 1.27 kg per meter cube. So this is quite large as compared to sigma. We can neglect this sigma to simplify our calculation. So let's put the value, and we know we are given the r to be 0.04 mm. So we can convert this into meter, and we are given the eta which is equal to 1.8 into 10 raised to power minus 4 poise, and we know the 1 poise is equal to 0.1 kg per meter second. So let's put all the values into this. So we can write this r to be 4 into 10 raised to power minus 5 whole square over 1.8 into 10 raised to power minus 5. This will become 1000. We are neglecting the sigma, and this is 10. So g is 10, our acceleration due to gravity. So let's simplify this. this will be 16, this is 1.8, and this is minus 10 plus 5 plus 4. So our terminal velocity will be 0.197. So we are coalescing the 100 drops together. So if one water drop radius is 0.04 mm, if we are joining the 100 such drops together, so we are equating the volume. So our water drop will become something like this. So this will be a radius r, and so we will calculate this radius. So we are equating the volumes. So the volume of the bigger drop, this having a radius r, capital R, will be equal to 100 times multiplied by the volume of a single drop. So this will be equal, so the volume will be 4 by 3 pi r cube, and this 100, and the volume of smaller is 4 by 3 small r cube. So r cube is equal to 100 times r cube. So we will be using this relation. So our expression for terminal velocity is 2 by 9 r square eta rho minus sigma g. So let's put all those values again. So here the small r will become the capital R. So this will be capital R. So because here we have a bigger drop. So this is 2 by 3 and this is r square. This is eta rho sigma times g. So our new terminal velocity will be 2 by 9 r square eta rho minus, this is the previous velocity, terminal velocity, and this, so we simply have to multiply by this 100 twice by 3 factor. So we know our previous terminal velocity is 0.197. We just multiply this and into 100 twice by 3. So our terminal velocity will come out to be 4.24 meter per second. So you can check if you have any doubts related to this, you can ask me in the comment box. If you find this video useful, please like, share, subscribe to my channel, and thank you for watching this video.